Hello and welcome to the first video of section 4.3 on the fundamental theorem of calculus. Mathematicians do not throw around the word fundamental lightly. In this section, we connect integration and differentiation, which allows us to compute definite integrals without calculating limits of Riemann sums. Like with derivatives, we will develop rules that will allow us to bypass limit calculations in all but a few cases. In this video, we focus on the first of the two parts of the fundamental theorem of calculus. Take the line f of x equals 1/2 x plus 1. Suppose we are interested in the area under f between 0 and 6. Since f is a line, we can calculate the area under the curve with regular geometric shapes, and we can avoid Riemann sums. We realize the region as a triangle above a rectangle. If we take the sum of the triangle and rectangle areas, we find the area under f on the interval. The base of both the rectangle and the triangle have length 6. The height of the rectangle is 1, and the height of the triangle is 3. The area of the rectangle, 6 times 1, plus the area of the triangle, half of 6 times 3, gives the area under f on the interval, which is 15. We calculated the area under f for a fixed interval. Suppose we took the boundary value of 6 and replaced it with a different value. What would change? Suppose we move the boundary value to 8. We would extend the base of both shapes by 2 units and increase the height of the triangle by 1 unit. We can generalize this by replacing the right boundary value with a variable. Let's call that variable t. Using the area of the triangle and rectangle, we obtain a of t, a function for the area under f on the interval 0 to t. Both shapes have base length t. The height of the rectangle is always 1, and the height of the triangle depends upon t, and can be expressed as f of t minus 1, or 1/2 times t. A of t equals the sum of the triangle and rectangle's area, which simplifies to 1/4 t squared plus t. Here is where we find the connection between derivatives and integrals. The derivative of the area function a of t is precisely the function f of t. That is, the derivative of the integral of f of t on the interval from 0 to x is equal to f of x. We've just discovered the fundamental theorem of calculus part 1. In class, a more rigorous explanation will be provided, but for now, let's discuss some consequences of part 1 of the theorem. As always, we start with the premise. The fundamental theorem only holds for functions on a continuous interval. So what can we do if the function isn't continuous? Well, that really depends on the types of discontinuities. If the function has a finite number of removable or jump discontinuities, then you can cut the integral's boundary along these discontinuities and use the first part of the theorem on the continuous pieces. If the function has an infinite number of discontinuities, or infinite discontinuities, then you cannot use the fundamental theorem at all. You can't avoid it anymore. You are forced to go back to the definition and take the limit of a Riemann sum. Part 1 of the fundamental theorem says that an antiderivative of a function f of x is the integral of f of t from any constant to x. You've seen the basics. Now work towards mastery through practice and study.